Okay, so these next two lectures, are going to be somewhat less example oriented. I just want to introduce the main definitions because those of you taking Math 5800 are going to need to know them, and they're important for that reason. Okay, let me remind you of where we are. So I want to recall where we are. We talked about the expected value of x. You have random variables x and y. We talked about the expected value of x given that y conditioned to y equals y. And we define this to be, in the discrete case, the sum over all x's of x times the probability, the joint probability mass function, pxy, xy, and that's in the discrete case. And in the continuous case, you had the integral from minus infinity to infinity of x times the density, the joint density, the conditional density function. Okay, so then we also described this, you might call it a partition formula, that tells you that the expected value of x can be rewritten in terms of these conditional expected values. So in the discrete case, it's the expected, you sum up the expected value of x given y equals y times the probability that y equals y. So I'll just write the probability mass function of y. So let me do it the proper way. Y equals y. That's in the discrete case. And in the continuous case, and what are we summing? We're summing over x's here. I'm sorry, you're summing over y's here. And in the continuous case, you're integrating from minus infinity to infinity the conditional expected value times the probability, the marginal probability density function of y. So we talked about this last time, and what I want to talk about is an application of this formula that I just wrote down in a very special case, and I want to introduce how to relate this back to events. Okay, so I'm going to make an application here to something that we saw way a long time ago. Okay, so let's consider S to be the sample space. That's the usual notation we use for it. And let A be a subset, so that's an event. A is an event. An event, recall, is just a subset. So now we can define a random variable based on A. So the random variable only takes two values. It's either 0 or 1. So chi sub A, x sub A of an element of the sample space is equal to 1 if S is in A, and it's equal to 0 if S is not in A. So this is the so-called indicator function, or the indicator random variable of A. Okay, so now how does this relate to the probability properties of A? Well, let's compute the expected value of this random variable. Well, let's see what we get. So this is the sum over all x's. I'm just going to handle the discrete case. The continuous case is exactly the same, except you integrate, of x times the probability that x equals x. But you see, x only takes two values. X sub A only takes two values. 0 or 1. And if x is 0, there's no contribution to the sum because you're taking 0 times something. And if x equals 1, well, you're going to get 1 times the probability that x sub a equals 1 appearing. But what does it mean? What is the probability that x sub a is 1? Well, that's the event which is given by all the elements in the probability of the event given by all the elements in the sample space whose value under the indicator function is 1. But that's exactly the probability of the event A. So this is equal to the probability of A. So we just, this is the significance of the indicator random variable. Its expectation is the probability of A. A similar thing we can actually compute is the conditionally. So it's a similar calculation, which I won't do. We get that the expected value of x sub a conditional to some random variable y taking value lowercase y. So the conditional expectation is the same as the probability of a subject to this. It's the same sort of idea. Okay. So now what does this tell us? This tells us the following. If we apply the the formula that I wrote on the previous slide, this tells us the following. So the probability of A, which we saw in, if you look at the green box, we get the expected value of x sub A. But the expected value of x sub A we saw was the sum, at least in the discrete case, it would be an integral in the continuous case, of the expected value of x sub A conditioned to y equals y times the probability of y equals y. So that's what you get. That's the sum, and you're summing over y. But what is that? We know from what I just did in the previous line that that's the same thing as the sum over y of the probability of A conditioned to y equals y times the probability that y equals y. Okay, so this is actually something we pretty much saw before. But I'd like to write down the continuous case as well of this formula. But let me circle this formula. The probability of A is given by this decomposition as a sum. Okay. Similarly, in the continuous case, we have a similar formula, which I'll just write down. It's the probability of A is given by the integral from -infinity to infinity of the probability of A conditioned to y equals y times the density function dy. Okay, so now actually there's a very special case of this. Okay, so let's consider the following special case of this decomposition. I want to suppose I've given A an event as before, and then we're given B1 through Bn mutually exclusive, whose union B1 union B2 ... union Bn is the entire sample space. So this is like a so-called partition of the sample space. You can think of it like this way. If this is the sample space, you have B1, B2, and so on ... B sub n. Okay, so these are we've cut up the sample space into disjoint sets. So let's define a random variable y going from real value random variable as follows. Let's define it to be y of s in S is given by k if S is in BK. And since the BKs are pairwise disjoint, S can only be in one such BK. So then BK is the same thing as the event given by y equals k. And so the probability of bk is the same as the probability that y equals k. And if we do the formula I got on the previous slide, we get the probability of A is given by the sum, k goes from 1 to n, the probability of A times the probability that y equals k, which is the probability of bk, times the probability of bk. So this was a formula we got a long time ago, which enables you to compute probability of A in terms of conditional probabilities on the right-hand side. So we've recovered that formula. Okay. So that's all I want to talk about in 7.5.3. So we're done. I don't want to talk about all the examples there. There are lots of them, and they would take a lot of time to cover. So I'm just this is all I wanted to talk about here. The next thing I want to talk about is 7.5.4. So 7.5.4 is called conditional variance. I'm just going to talk about definitions here. I just want to remind you, we talked up till now about conditional expectation. So let me remind you, is we can recall that if we can talk about the expected value of x given y, it's a function of y. That is, we can talk about the expected value of x given that y equals lowercase y. That's a well-defined thing, and we defined it as, in the discrete case, as the sum of x, the probability mass function of x, y. This is the conditional probability mass function. In the discrete case and in the continuous case, it's the integral from minus infinity to infinity of x, p x, y, x, y, dy, dx. Okay, so that's what it is. And we also know from what I did last time that the expected value of x can be recomputed as the expected value of the expected value of exy. Exy is a random variable. So, and this was related to our partition formula that I talked about today. Okay, so today, in this section, 7.454, we have, instead of expectation, we can talk about a version of variance. We do variance. Okay, so I want to, I need some space for this, so let me get it. Okay, so here's what I'm going to do. I'm going to make a definition. So it goes like this. The conditional variance of x with respect to y, or the variance of x conditioned to y, is given by, this is the definition, it's given by the expression variance of x conditioned to y. It's the expected value of x squared conditioned to y minus the expected value of x conditioned to y, and we square it. So it looks very similar to the unconditioned version. And I want to relate this. Remember, we had this formula that said the expected value of the expected value of x conditioned to y is the expected value of x. I erased that, it's on the previous slide. There's a version for the variance. So this is the so-called conditional variance formula, which I want to derive. Okay, so here goes. So it says this, if I want to compute, this is proposition 5.2 in the text. It says this, if I want to compute the variance of x, I can do it in terms of these conditional variances as follows. I take the expected value of the variance of x conditioned to y, which the variance of x conditioned to y is a random variable, and I add to it the variance of the expected value of x conditioned to y. So in the first case, in the first summand of the right-hand side, I have the expectation after the variance, and the second term is the variance after the expectation is on the inside, the variance is on the outside. So I'm going to give you a proof of this, okay? So here's a proof. The proof goes like this. Okay, so first of all, let's use what we did already. Namely, we know that E of x from my previous lecture is given by the expected value of the expected value of the conditional x conditioned to y. So we're going to use that. Okay, so first of all, there are two steps in the proof. Step one is to calculate the variance, the second term on the right. So the variance of the expected value of x conditioned to y. Well, the variance is by definition of any random variable. Z is the expected value of the second moment minus the square of the expected value. So this would be the same thing as the expected value of the random variable on the inside, which is EXY. Okay, we have to square that minus the expected value of the expected value of xy, but now the squaring is all on the outside. But now we know that this term here is E of x quantity squared. We saw that from here. Okay, so that's the first term. That's the second term on the right side. Now let's go to the first term on the right side. So 2. Let's calculate the expected value of the variance of x conditioned to y. Well, we know what the variance is. Again, it's the same thing. We have it as the expected value of the, this is what we defined up here. This use the definition. The variance of x conditioned to y is E of x squared conditioned to y minus EX conditioned to y squared. But the we know that we know that the expected value of a difference is the difference of the expected value. So you're going to get E of x squared conditioned to y minus E of x conditioned to y squared. Okay, so now what do you get? Well, the first term here, I'll circle it in yellow, by this formula applied in a different situation where x is replaced by x squared gives me E of x squared. So this term is E of x squared. And this term here that you get does not go away. It's the same as the term above. So when you add these together, 1 plus 2, you get cancellation. This term and this term cancel, these two terms pointing to each other by the yellow arrows, and you're left with E of x squared from here, and then minus E of x squared from there, which is the variance of x, and that's what we had it to show. So we've proved it. Okay, so that is the conditional variance formula. Okay, so that's enough of that. We have one more section to cover in chapter 7 that I'm going to cover, which is 7.7, which is called moment generating functions. We're going to cover that also in a very shallow way. That's it for today.